There's this idea in machine learning, and honestly, you see it everywhere in life too. This idea that if you just um, optimize for the big picture, the details will sort of work themselves out.
The good enough approach. Get the general vibe right and don't
Sure.
sweat the small stuff.
Exactly. But it's becoming this real crisis of alignment in things like natural language processing. We're building these huge models, training them to maximize some, global score.
Mm,
And then we act all surprised when they make these really specific granular mistakes. It's like studying for a test by just memorizing the pattern of the answer key A, C, B, D without actually learning any of the material.
that's a perfect analogy. It's the classic disconnect between your training objective and your evaluation metric. You're training for one thing, but you're being graded on something completely different.
And today we're doing a deep dive into a paper that just tackles this problem head on. It's called Labelwise Margin Maximization for Sequence Labeling. It's by Wenjin Gao, Xipeng Qiu, and Xuanjing Huang from Fudan University.
And their core premise is really simple, but powerful.
hmm
They argue we should stop trying to be right on average and start focusing on being right specifically at every single point.
It's a move away from this global focus, which has been the standard for, what, a decade?
At least. And they're bringing it back to a kind of local optimization, but with this really clever twist they call label-wise margin maximization, or LPA.
So before we get into what LPA actually is, we should probably set the stage with the status quo. I mean, for years, if you were doing sequence labeling,
And by sequence labeling, we mean tasks like part-of-speech tagging. Is this a noun, a verb, an adjective?
right, or named entity recognition, chunking text,
You were probably using a conditional random field,
a CRF.
a CRF, yeah, or
Yeah.
maybe a maximum margin Markov network, an M3N.
Right. And the reason those models were so dominant is that they handle dependencies between labels really, really well.
What do you mean by dependencies?
Well, think about the phrase New York. If a model just looks at the word new by itself, it might label it as an adjective.
But a CRF looks at the whole sequence. It sees that York follows new, and it knows that New York together is almost always a location. So it labels the whole chunk correctly because it considers the context.
That makes a ton of sense. Context is key. But here's the problem the researchers point out, and it's a big one. The way we grade these models is almost always something called Hamming loss.
Which is really just a fancy way of saying count up the mistakes.
Exactly. Hamming loss doesn't care about the overall probability score or how confident the model was about the sentence as a whole. It just looks at position 1, correct or wrong, position 2, correct or wrong. It's a pass-fail at the micro level.
And that's where the conflict comes in. The CRFs, the M3Ns, they optimize for the likelihood or the margin of the entire sequence. They want the whole path to have a high score.
But the paper says that this global objective is, and I'm quoting here, inconsistent with the evaluation measure.
They have this brilliant example in the paper, it's figure 1, that just perfectly illustrates this. I mean, it really breaks the intuition we've all been taught about margins.
Yeah, let's walk through it. It's a Chinese word segmentation task. So you have a sentence, call it X. And for that sentence, you have a correct sequence of labels and a wrong sequence of labels.
And the model is trying to decide between two different sets of parameters. Let's call them parameter 1 and parameter 2. Which brain is better?
Okay, so parameter setting 1 gives a total margin score of 9, and parameter setting 2 gives a total margin of 12.
So, in standard machine learning, a bigger margin is better, right? It means more confidence, better generalization. Any traditional algorithm, like an M3N, would look at the 12, look at the 9, and pick the 12. It's a no-brainer.
But hold on, let me play the traditionalist for a second. Why is that wrong? If the model scores a 12, it means the gap between the right answer and the wrong answer is wider. That should be a good thing. Why would we ever want the weaker score of 9?
Because you have to look at how that score is actually built. This is where the whole global view can hide some serious problems.
Oh.
In that first parameter set, the one that scored a 9, every single individual label in the sequence contributed a small positive margin. Say they were all +1s. The model was a little bit confident about everything being correct.
So consistent, but maybe not super confident.
Exactly. Now, in the second parameter set, the one that got the big score of 12, you might have some labels where the model is screaming with confidence, like a margin of +4. But then you have another label in that same sequence with a margin of -1.
A negative margin? What does that even mean?
A negative margin means the model actually preferred the wrong label at that specific position. It made an error. But because the other labels in the sentence were so confident, those big +4s, it completely drowned out that one mistake. The total sum is 12, which looks fantastic on the surface, but the model actually got a word wrong.
So the high total margin is masking a local failure. It's like a student who gets an A on a group project because their partners did all the work, even though that student failed their specific section.
That's it exactly. And since we're graded on Hamming loss, which counts every single error, parameter 2 is actually the worst model. It produces 1 error. Parameter 1, despite its lower confidence score, produces 0 errors.
That is such a critical insight. We've been optimizing for the sum, just assuming the parts would fall in line, but the sum can lie.
It can absolutely lie. And so this leads us directly to their solution, LPA. They just decide to decompose the problem.
Decomposition, okay.
Instead of trying to maximize the margin for the entire sequence in one go,
Right.
they break it down. They aim to maximize the margin for each individual label.
But doesn't that feel like we're taking a step back? We just talked about how important context and dependencies are. If we just look at each label in isolation, don't we lose that whole New York thing we mentioned?
See, that's the really clever part. They're not actually ignoring the structure. The model is still a structured prediction model. But the loss function, the thing that tells the model how to learn, is what changes. It forces every single label individually to satisfy a margin constraint.
And how do they do that?
They build it on top of an existing algorithm called the Online Passive-Aggressive Algorithm, or PA.
Oh, yeah, I love the PA framework. It's so practical for online learning. The passive part means if the prediction is correct, the algorithm does nothing, right? Don't fix what isn't broken.
Exactly. And the aggressive part means if you make a mistake, you update the model's weights just enough to fix that specific error and no more.
So it's efficient.
Very.
Ah.
But the researchers here modified it. They came up with something they call a label-wise hinge loss. Normally, hinge loss is global. Did the correct sentence score beat the wrong sentence score by some margin?
Right.
They changed it to, did the correct label at position? I beat the most confusing wrong label at position I by some margin.
So they're basically running a tiny optimization problem for every single word in the sentence.
Yes. And from a math perspective, this is where it gets interesting. They use Lagrangian multipliers to solve this.
Which implies there's a constrained optimization happening.
There is. You think of it like this. The algorithm's main goal is to update its weights to fix any errors it made. But it has a constraint. It wants to change those weights as little as possible so it doesn't forget everything it's already learned.
Ah, so it's a balance. Correct the new mistake without messing up old knowledge.
Precisely. And the Lagrangian helps find that perfect balance. The paper also mentions they solve a linear system using SVD singular value decomposition. That's just the mathematical engine they use to crunch the numbers and find the optimal update for the weights.
Okay, so we have a mathematically robust loss function that is absolutely ruthless about getting every single detail right. But the big question is always, does it actually work in practice? Theoretical elegance doesn't always survive contact with messy, real-world data.
Right. The proof is in the pudding. They ran 3 main experiments, comparing their LPA method against state-of-the-art models like CRF, M3N, and the standard PA algorithm.
Let's start with the first one, text chunking on the Wall Street Journal corpus.
This is the Conello 2000 shared task, a classic NLP benchmark. The goal is to identify phrases, like noun phrases or verb phrases, and LPA achieved an F1 score of 94.11%.
Okay, but I have to play devil's advocate here. They compared that to a CRF, which got 93.79%. That's a difference of, what, 0.32%? Is that really significant, or could that just be noise?
That's a very fair question, and on a brand new data set, I'd say, yeah, it might be noise. But the Wall Street Journal corpus has been a benchmark for 20 years. It has been hammered on by researchers. The low-hanging fruit is long gone.
So squeezing out any extra performance is tough.
Extremely tough. Getting another 0.3% over a super strong CRF baseline is actually considered a big deal in the NLP community. It suggests you found a genuine structural advantage, not just a lucky parameter setting.
That's a good point. Breaking a plateau is harder than climbing the initial hill. But I think the second experiment is where this method really gets to show off. Chinese word segmentation.
Yeah, this is a much, much harder task. In English, we have spaces that give us a huge head start on where words begin and end. Chinese is just a continuous string of characters.
So the ambiguity is way higher.
Way higher. You mess up one boundary, and you can completely change the meaning of a sentence. They tested this on 4 different data sets from the Sagan Bake-Off 2.
And what were the results?
LPA came out on top across the board. But the most telling comparison for me was against the standard passive-aggressive algorithm. Remember, LPA is basically PA, but with these extra local constraints added on.
Right.
LPA gave about a 2% improvement over the standard PA.
Wow, okay, a 2% boost is not noise. That's the massive improvement.
It's huge, and it really confirms their core hypothesis. The standard PA, with its global view, was getting confident about the wrong things. By forcing those label-wise constraints, LPA just cleaned up all those internal errors.
The paper has these graphs, figures 2 and 3, that show the per-label accuracy.
Yes, and if you look at those plots during training, the LPA line is just consistently above the others. In Chinese segmentation, you're labeling characters as either the beginning of a word, the middle, the end, or a single character word.
BMES.
Right. And a global model might learn a really strong pattern for a common multi-character word. It gets so confident that it might try to force that pattern to fit even when the context is wrong. LPA checks every single character and asks, is this really a beginning character? It prevents the model from just coasting on memorized phrases.
It stops it from overfitting to common word combinations. Now, speaking of overfitting, they mentioned using averaging technology. What's that about?
Averaging is a common regularization trick in these kinds of online learning algorithms. Instead of just using the final set of weights you get after training is done, you average the weights from every step of the training process.
And that helps it generalize better.
Yeah, it stops the model from being too biased by the last few examples it saw. It makes the final model more stable and robust.
Got it. And the third experiment was on named entity recognition.
NER, yeah.
Hmm?
Finding names of people, organizations, locations. And again, it was a solid win for LPA. On one of the main data sets, it hit 81.78%, while the CRF was back at 79.58%. That's over 2-point F1 improvement.
That's significant.
It is, and NER is a great example of why this works. Most words in a sentence are not part of a named entity. They get the label O for outside.
Right, the boring majority.
Exactly. So a global model can get a really high accuracy score by just getting good at predicting O all the time. But LPA, with its label-wise focus, is forced to pay attention to those rare but important tags like beginning of person or inside of location. It can't hide behind the easy labels.
That makes so much sense. The global margin is dominated by the easy cases, but the local margin gives a voice to the rare and difficult ones.
You could say it democratizes the loss function. Every single token gets an equal vote.
So if we try to wrap this all up, what's the big takeaway for someone listening who's building models day to day? I mean, we're not all building Chinese word segmenters from the ground up.
I think the lesson is to really, truly audit your loss function. We so often just grab an off-the-shelf loss like cross-entropy or a standard max margin because it's the default in whatever framework we're using.
Sure, it's easy.
But you have to step back and ask, does this loss function actually mirror what I consider success for this task? If you care about every single prediction being right, and that's true for things like medical diagnosis or fraud detection, then you might need to think about these kinds of label-wise local constraints.
It's the difference between saying the patient is generally healthy and saying the patient has a specific critical issue in their left ventricle. The average score doesn't really help the patient.
Exactly right. And this paper proves you don't have to give up the benefits of structured prediction to get that local precision. You can have both. You just have to decompose the margin.
It's a really compelling argument, and it makes me think about this whole paradox of high margin, low accuracy. We see this with large language models now, don't we?
We do.
They can be incredibly confident in their hallucinations. They'll state something that is completely wrong with absolute authority. Do you think this label-wise idea could apply there too?
That is the billion-dollar question, isn't it? Well, think about how we train them. They start with next token prediction, which is very local. But then we fine-tune them with things like reinforcement learning from human feedback, RLHF.
Right, and that's often a judgment on the whole response, like, was this a helpful answer?
Yes, it's a global judgment. And we might be accidentally training them to have a high global margin to sound, convincing and coherent overall, even if specific facts within the response are totally made up.
A hallucination.
A hallucination. So what if you applied a label-wise margin concept to RLHF? What if you didn't just rate the whole answer, but you specifically penalize individual factual errors within a generated paragraph? That could be a powerful way to start fixing the hallucination problem.
That's a fascinating thought. We're training them to be smooth talkers when maybe we should be training them to be fact checkers, one fact at a time.
This paper was about sequence labeling, but that core philosophy, don't let the whole hide the flaws in the parts, that feels like it could apply almost anywhere.
The devil, as they say, is in the details.
And maybe the solution is too.
We'll have to leave it there. A huge thanks to the researchers Gao, Q, and Huang for this fantastic work. And thank you for joining us for this deep dive. If you're out there building models, maybe take a second look at your margins today.
Keep optimizing.
We'll see you next time.